Alright guys, welcome to your Princeton Review help videos. This is for week 18. And we're starting off on page 97 with number 7. Alright, so the first thing that we're going to try to do here is we're going to try direct substitution first. That's always how you try a limit at first. So that's, if I plug in 6 to the top, I'm going to end up getting 8. If I plug in 6 to the bottom, I'm going to get 36 minus 24 minus 12. And I end up with 0 on the bottom. And that's not allowed. And so direct substitution fails. Now when direct substitution fails, we have some other options. The other option would be either L'Hopital or factoring. Now we can't use L'Hopital, because L'Hopital only works when you have 0 over 0 or infinity over 0, and we don't have that. We have 8 over 0. So in that case, you could try factoring it. But usually, if L'Hopital doesn't work, factoring is not going to work either. But I'll try to factor it really quick, see if that works. Does that work? All right, let's make sure that all works out. Negative 12, that's going to be negative. Okay, cool. Yeah, I factored it right. It looks good to me. Let's see, though. Those cancel out, and so now I'm left with this. Now, even though we canceled something out, the problem is, even though something cancels out, there's still a problem, because the thing that we canceled out isn't the problem. The problem isn't whenever I plug 6 into this. That doesn't give me a 0. The problem is when I plug 6 in here, and that's still there. So I've done my factoring method, and we still have a problem. We still end up with 1 over 0, which is no good. And we also have established that L'Hopital won't work. So direct substitution didn't work. Factoring doesn't work. L'Hopital doesn't work. And for expressions like this, that's pretty much all we can do. So what that means is that this thing, the limit doesn't exist. But that doesn't necessarily mean we're going to stop there. That just means it's a non-removable discontinuity. And so when we have a non-removable discontinuity, what we do is we plug in a number that's really, really close to the number 6 and see, does it seem to be going into infinity or negative infinity? Now, since we're approaching 6 from the left, I'm going to take 6 and I'm going to subtract from it a really small value. And that would give me 5.999. So what I'm going to do is I'm going to plug 5.999 into this function. And I'm going to see what I end up with. Now, if I end up getting a positive number, then that indicates that the function is approaching negative infinity. But if I get a negative number, that means my function is approaching negative infinity. Okay? So let's go ahead and do that real quick. I'm going to punch this in my calculator. I'm going to pause my video so you guys don't just wait for me to click buttons. So just a moment. So after working that out, by picking a number that's really, really close to 6 on the left side, I end up with negative 1,000. And what that tells me is that as my function is getting closer, as x is getting closer and closer to 6 on the left side, my function is approaching a value of negative infinity. Okay. Now, to do number 8, we already know that this is a non-removable discontinuity. So we have 3 possibilities. Well, actually, we only have 2 possibilities. It's either negative infinity, or we're just going to say it doesn't exist. Now, here's how you'll know the difference. I found the limit from the left, but now I want you guys to find the limit from the right. Find the limit from the right of that function. If you do that and you get negative infinity, that means the answer is negative infinity, because the limit from the left and the right are both going to infinity. But if you end up getting a positive infinity, then we're going to say it doesn't exist, because the limits on the left and right are going in different directions. Okay? But I'll leave you guys to find the limit from the right using a similar strategy. The only difference is you add 0.001 instead of subtracting it. Okay, let's move on to page 110, numbers 5 and 6. Is the function f of x equals secant of x continuous on this interval? A little while ago I gave you guys a handout called the continuity of common functions. And it looks like this. And so if I want to know where this function is continuous and where it's not continuous, I'm going to go down, I'm going to find where secant is. Secant's right here. And there are discontinuities for anywhere where the inside of your secant function, a of x, is equal to pi over 2 plus any multiple of pi added to it after that. Let me write that up here really quick. We have discontinuities. Anytime the inside of my secant, which in this case is just x, anytime x is equal to pi over 2 plus a multiple of pi. Okay? So let's go ahead and start off at this pi over 2 here. And let's make n a negative number. So -1. So what happens if we subtract a pi from it? First of all, we need to get a common denominator. And then 1 minus 2 leaves me with -1 pi over 2. So from here to here, these are both discontinuities. But the question is there anything in between it? Well, no. I plugged in -1, and that took me right from this one to the one right after it to the left, and it just takes me to this next endpoint. So there's nothing in between here where it would have any discontinuities. And so the answer is yes, it is continuous. All right. For number 6, this is a pretty common function here, or a pretty common question. They want to know, is it continuous? So, both of these are polynomials, so those are always going to be continuous. But the question is it continuous at x equals 4, where these two pieces are connecting together? Okay? And the only way to determine that is by finding the limit from the left of 4 and seeing if it matches the limit from the right of 4. All right. Now, if I'm approaching 4 from the left, I would be using this top piece here, 3x squared minus 11x minus 4. And the limit from the right, I'd be using the bottom piece, which is kx squared minus 2x minus 1. And we want to find the value of k that makes these two things equal. So we're just going to plug our 4 in to both of these equations for x. All right. So this is 16 times 3 is 48 minus 44 minus 4. 16 times k is going to be 16k. Minus 8 minus 1 is minus 9. Putting all these things together here, we end up with 0. Oops. So I'm going to add 9 and divide by 16, and I end up with 9/16 as my answer. All right. So we're on page 131 now. We're going to do numbers 8 and 9. I'll do number 8 and I'll let you guys do number 9. The directions are asking us to find the derivative of the expression. So we want to find the derivative of this thing. Now before I start, I'm going to go ahead and make sure that that radical is rewritten a little bit differently. I'm going to rewrite that as x to the 1/2 power. Actually, you know what? I'm going to use a shortcut. I'm not going to rewrite it. I want you guys to get used to the shortcut. A lot of you guys don't like the shortcut because it's one of those things you have to memorize, but once you have it, it's really nice to know. So let's go ahead and just skip the rewriting process, and I'll show you how to do it using a shortcut. So the derivative of this, you're going to multiply negative 8 in the front by the negative 8 exponent. So it's going to be negative 8 times negative 8, which is 64. And then you're going to take 1 away from the power there, so it'll be negative 9. Then we have 12. And when you take the derivative of square root, it's always going to be 1 over 2, and then that same square root just goes in the bottom. And then you're going to multiply it by the derivative of the inside. In this case, the derivative of x is just 1, so it doesn't really matter. So if we were to rewrite it, it would look like this. And then the 12 over 2 can reduce. And that's good enough. I don't think we need to go any further. They might choose to put this x to the 9th over here on the bottom as a positive. I'm not sure, but it doesn't really matter. Just want to make sure you guys know how to find those derivatives. So I'm going to go ahead and leave number 9 for you guys. Let's go ahead and move on to our next page. All right, so we're on page 139 now. And we're going to be doing numbers 8 and 9. Now I'm going to let you guys do number 8 because it's a little bit more simple. But I'm going to do number 9. Number 9 is a little messier. But I'm not going to actually ask you guys to simplify it. I want you guys just to go ahead and do the derivative and then leave it. Don't try to simplify it. I know the back of the book has it all simplified, but it's just kind of a time killer. And I don't think you guys are going to be expected to do anything like that on your AP exam. It's a waste of time. So just want to make sure you know how to find these derivatives. Now what 8 and 9 have in common is the fact that they are both chain rules. And what I mean by that is they have an inside function and they have an outside function. Okay? Now, there's a couple of ways that you could do this. One way you could do this is, let's go ahead, well, basically the first thing you want to make sure you understand is that you always do the derivative of the outside multiplied by the derivative of the inside. Now, the derivative of the outside, there's two ways you guys can write your answer. One way is using the little shortcut I just shared with you. The shortcut I shared with you is it's always going to be 1 over 2 times the square root of the same exact thing that you just did. Okay? That's one way you guys can write that. Another way you guys can do it, if you want to do it the other way, which is a little bit more work, is you can think of this square root here. You can think of the square root as parentheses with a half power, in which case you would move the half to the front. You would leave the inside the same. And then you would take 1 away from your power, which is negative half. And that expression is literally the same thing as what I had just up there a second ago. It's just that instead of a square root, it's a half. And instead of being in the denominator, it's written next to it with a negative exponent. But it's literally the same expression. I just like the shortcut. So you guys can use either one you want to. But either way, that's the derivative of the outside. Now I want to multiply it by the derivative of the inside. Now the inside is a fraction, a rational expression. And the way that you find the derivative of a rational expression is you do the quotient rule, which is low d high minus high d low, draw a line and square below. So low d high minus high d low. Draw a line, square below. And that's where I'm going to stop with this problem. You can definitely simplify this, but it's not worth it. It's just pointless. It's basically just showing off some amazing algebra skills to try to simplify it. I don't care about that right now, and I don't think that you'll ever be asked to do something like that. So we're not going to worry about it. That's good enough. There's our derivative. Same thing whenever you guys do your number 8. After you apply the chain rule, you can stop and leave it there. You don't need to simplify it, okay? Let's move on to our last page. All right, for page 149, we're going to do 6 and 7. So I'm going to start off with 6. Here we go. So we want to find the derivative of cosecant of x squared. All right. Well, I'm going to start by rewriting this. Cosecant of x squared squared. Well, I don't like where they put the square in trig functions. I like to write it like this because that's what it really means. So we're taking cosecant of x squared, and then whatever that is, we're squaring that. That's what it means when they put that little 2 right there. So I like to put brackets on it and move that little 2 to the outside of the bracket so it looks a little bit more like what it really is. Now, this is what we called back in September or August, what I called the egg rule. Because you have yolk, you have egg whites. No, I'm sorry, egg white. This is the shell, my bad. You have the shell, and then you have the egg whites, which I'm not going to write in white because it'll be hard to see, so I'll make it purple. But basically what this is a double chain rule. You have an outside function that I've drawn in kind of like a peachy color there. You've got a super inside function there, which is what I've colored yellow. And then you have a function that's inside of the outermost function, but it has the yellow one inside of it, and that's the purple one. So you have a function inside of a function inside of a function. And so when you do this, you're going to do your chain rule, but this time instead of the derivative of the outside times the derivative of the inside, it's the derivative of the egg whites multiplied by the derivative of the, I keep saying egg whites. Let me back up. I know you guys know what I mean, but I'm just being picky here. So it's the derivative of the shell times the derivative of the egg whites times the derivative of the egg yolk. And we're multiplying all 3 of those together. Okay? So now as for the egg white, the peach colored drawing here, that's just a power rule. So you're going to take your power, you're going to move it to the front, and you're going to subtract 1 from the power, which makes it a 1. And then everything on the inside just stays the same. Okay? Now we do the derivative of the purple part. The derivative of cosecant is cosecant, actually it's negative cosecant, cotangent. And whatever's on the inside stays the same, so x squared. Move these little multiplication dots here so they're in a better spot. And then finally we multiply that by the derivative of the innermost function there, the x squared, which is just going to be 2x. All right? So there's our answer. Now we could kind of simplify this a little bit. So how can we simplify this? Well, first of all, this 2 and this 2, I can multiply those together and make it 4. Also the x, I would want to put that in the front with the 4. So it's going to look like this, 4x in the very front. So that takes care of these. I've put those together. Now we also have a cosecant x squared here and a negative cosecant x squared here. So if I put those together, I'm going to have a cosecant of x squared being squared. But now that I'm writing my final answer, I'm going to put the square where they usually like to put it, which is right there. And the negative that we had, I'll just put that in the very front. And then finally we have the cotangent of x squared right here. So I think this would probably be how the answer would be written on a multiple choice test, if you will. For number 7, you guys are going to be finding the derivative, the 4th derivative, which means you're going to be finding the derivative of this 4 times. But just make sure that you know, every time you take the derivative of this, it is a chain rule. You have the derivative of the outside being multiplied by the derivative of the inside. Okay, so I'll let you guys see if you can work that out and get the final answer for that one on your own. But other than that, I'm going to go ahead and stop there. Hope it was helpful, and we'll see you guys later.